Imagine yourself drifting silently in the vastness of space. Before you, a galaxy spins, a luminous whirlpool of billions of stars, gas, and dust. The core glows brilliantly, surrounded by spiraling arms stretching out like cosmic ribbons. It's a mesmerizing dance of light and motion held together by a gravitational force so immense it defies comprehension. Yet, hidden within this stunning spectacle is an enigma. The visible elements of the galaxy, stars, planets, and nebulae account for only a fraction of the mass needed to sustain this intricate ballet. What is holding these celestial bodies together? What invisible force anchors the galaxy's swirling arms, ensuring it doesn't fly apart? This is the mystery of dark matter, the unseen framework of the universe. It doesn't emit light or energy, making it undetectable by traditional telescopes. Yet, its gravitational pull shapes galaxies, clusters, and the universe itself. It is the scaffolding upon which the cosmos is built. The idea of dark matter arose when astronomers noticed discrepancies between what they could see and the behavior of galaxies. In the 1930s, observations of galaxies in the Coma cluster revealed they were moving faster than expected. Calculations showed that visible matter alone couldn't generate enough gravity to hold the cluster together. There had to be some missing mass, providing the necessary gravitational glue. Decades later, studies of spiral galaxies confirmed this phenomenon. Stars on the outer edges of galaxies were moving just as fast as those near the center, a behavior impossible under the laws of gravity, unless there was an unseen mass extending far beyond the visible boundaries. This realization reshaped our understanding of the cosmos. Today, scientists estimate that dark matter constitutes roughly 27% of the universe, dwarfing the mere 5% made up of ordinary matter. The rest, even more mysterious, is dark energy. The invisibility of dark matter sets the stage for one of science's greatest pursuits. It's a riddle that challenges the boundaries of our knowledge, compelling us to peer deeper into the fabric of reality. What is this unseen force? How does it interact with the visible universe? And what does its existence mean for our understanding of life, existence, and everything in between? The hunt for dark matter isn't just about solving an abstract puzzle. It's about uncovering the fundamental truths of the universe. If we can understand this invisible force, we might unlock secrets about how galaxies form, why the universe expands as it does, and perhaps even glimpse the forces that shaped the cosmos in its infancy. This is the unseen force shaping our universe. It surrounds us, permeates us, and holds the cosmos together. To understand dark matter is to understand the universe itself. To uncover the presence of something unseen, scientists rely on the subtle traces it leaves behind. One of the most compelling pieces of indirect evidence for dark matter comes from the phenomenon of gravitational lensing, a striking consequence of Einstein's theory of general relativity. Gravitational lensing occurs when the gravity of a massive object, like a galaxy or cluster of galaxies, bends the path of light from a more distant source. This bending creates distorted, magnified, or even multiple images of the background object, much like a glass lens does. When astronomers measure the extent of this lensing, they find something peculiar. The visible mass of the galaxy or cluster is far too small to account for the degree of light bending. The gravitational pull needed to create these effects is immense, far greater than what observable matter could produce. This discrepancy points to the presence of an unseen mass surrounding and permeating these galaxies. Dark matter, though invisible, exerts a gravitational influence that reveals itself through these cosmic distortions, allowing astronomers to see its effects, even if they can't directly observe the matter itself. Another key piece of evidence for dark matter comes from the rotation curves of galaxies. Graphs showing the velocity of stars and gas as a function of their distance from the galactic center. In a galaxy governed solely by visible matter, you'd expect stars further from the center to orbit more slowly, similar to how planets in our solar system move. This is because gravity weakens with distance, and the mass producing the gravitational pull would primarily reside in the dense, star-filled core. However, observations tell a very different story. When measurements were taken of the rotation speeds of stars in spiral galaxies, it was found that these velocities remain nearly constant, even at great distances from the galactic center. This flat rotation curve implies the existence of a vast, unseen halo of mass extending far beyond the visible stars. Without this invisible matter, the stars at the outskirts of the galaxy should be flung off into space, unable to maintain their high velocities. The logical conclusion: a massive halo of dark matter envelopes the galaxy, providing the necessary gravitational pull to stabilize the outer stars. Gravitational lensing and galaxy rotation curves are two sides of the same coin, each offering a glimpse of dark matter's pervasive role in the universe. Together, they form a consistent narrative. There is far more to the cosmos than meets the eye. Dark matter doesn't just shape individual galaxies, it influences entire clusters. In fact, gravitational lensing studies of massive galaxy clusters reveal intricate maps of dark matter's distribution, showing how it congregates in enormous structures that act as the scaffolding of the universe. These clusters themselves are stabilized by dark matter's immense gravitational influence, just as individual galaxies are. These indirect observations highlight the ingenuity of science. Without the ability to see or directly interact with dark matter, researchers rely on its gravitational footprints to trace its existence. Each distorted image and unexpected star velocity is a clue, bringing us closer to understanding the unseen. While the nature of dark matter remains elusive, these pieces of evidence confirm its presence beyond reasonable doubt. Dark matter is not a theoretical abstraction. It is a tangible force shaping the universe. Its detection may be indirect, but its impact on the cosmos is undeniable. Dark matter is enigmatic, not just because it's invisible to the naked eye, but because it interacts so weakly, if at all, with ordinary matter. This makes its direct detection an extraordinary challenge, requiring experiments of unparalleled sensitivity and precision. Despite these hurdles, scientists have devised ingenious methods and cutting-edge facilities to attempt what might seem impossible: capturing evidence of dark matter directly. The world's most powerful particle accelerator, with its 27-kilometer ring buried underground, smashes protons together at nearly the speed of light, creating conditions similar to those that existed moments after the Big Bang. These high-energy collisions produce a cascade of particles, which are meticulously analyzed by detectors to search for anomalies, potential fingerprints of dark matter. Scientists are particularly interested in detecting weakly interacting massive particles, WIMPs, a leading candidate for dark matter. The theory suggests that WIMPs might be created during these collisions. If WIMPs exist, they could appear as missing energy in the data, escaping the detectors without interacting, much like neutrinos. While no conclusive evidence for dark matter has yet emerged from these experiments, they have provided valuable constraints, narrowing the range of possible properties that dark matter could possess. The search continues with upgraded detectors and refined collision parameters, as researchers hope to one day spot dark matter particles among the debris of their high-energy collisions. Deep underground, shielded from cosmic rays and other background noise, lies one of the most sensitive instruments ever built to hunt for dark matter. Located in an underground research facility, this detector relies on a tank filled with ultra-pure liquid xenon to detect the faintest interactions between dark matter particles and normal matter. The principle is straightforward but ambitious. If a dark matter particle passes through the detector and collides with a xenon nucleus, it will produce a minuscule flash of light and a small ionization signal. These signals are then captured by ultra-sensitive photomultiplier tubes, capable of detecting even the faintest whispers of activity. Although this detector has not yet observed definitive evidence of dark matter, its results have set new benchmarks for sensitivity, helping to rule out certain theoretical models. Its successor, with a larger detector and enhanced capabilities, is even more advanced, sifting through the cosmic silence in search of dark matter's elusive presence. Beyond these experiments, numerous other projects contribute to the hunt for dark matter. These employ different approaches, from cryogenic detectors to bubble chambers, to maximize the chances of detection. Each of these experiments tackles a specific aspect of the dark matter puzzle, reflecting the global collaboration and interdisciplinary innovation required to confront this profound challenge. The diversity of techniques ensures that even if one method fails, others may succeed in uncovering dark matter's secrets. The direct detection of dark matter would mark a watershed moment in physics, confirming the existence of a previously invisible component of the universe. It would provide not only answers to long-standing questions, but also open doors to entirely new realms of understanding. For now, the search continues, a testament to humanity's unyielding curiosity and determination to reveal the unseen forces shaping the cosmos. Detecting dark matter is one of the greatest challenges in modern physics. By its very nature, dark matter defies direct observation. It does not emit, absorb, or reflect light, nor does it interact with electromagnetic forces. Its presence can only be inferred through its gravitational effects, making the search akin to hunting shadows in a darkened room. Yet these obstacles have not deterred scientists. Instead, they have fueled ingenuity, pushing the boundaries of technology and theoretical physics. The prevailing hypothesis suggests that dark matter interacts only through gravity and possibly the weak nuclear force. If true, this means that dark matter particles pass through ordinary matter almost entirely unnoticed. For context, billions of dark matter particles could be streaming through your body at this very moment, leaving no trace of their passage. This weak interaction necessitates detectors of extraordinary sensitivity. These instruments must distinguish potential dark matter signals from a cacophony of background noise, including cosmic rays, neutrinos, and even natural radioactivity in the Earth itself. To overcome this, experiments are often placed deep underground or in remote locations to minimize interference. The pursuit of dark matter demands cutting-edge technology, which comes with significant costs. Facilities like the Large Particle Collider and underground detectors require immense financial and logistical support. Furthermore, the sheer complexity of these instruments means that even minor malfunctions can delay research for months or years. For instance, liquid xenon detectors must maintain extreme purity to avoid contamination that could mimic dark matter interactions. Achieving this level of precision requires meticulous engineering and constant monitoring, making every experiment a balancing act between innovation and practicality. One of the greatest challenges in the hunt for dark matter is the uncertainty surrounding its nature. While theories like WIMPs dominate the conversation, other candidates, such as axions, sterile neutrinos, and primordial black holes, offer competing possibilities. Each theory demands a different experimental approach, dividing resources and efforts. Moreover, if dark matter does not conform to these existing models, scientists may be searching in the wrong direction entirely. The possibility that dark matter interacts via unknown forces or consists of particles beyond the standard model of physics remains an ever-present challenge, forcing researchers to constantly reevaluate their assumptions. Dark matter is not evenly distributed throughout the universe. It clusters in halos around galaxies and galaxy clusters, but its density varies significantly depending on location. Detecting dark matter on Earth might therefore be akin to searching for a single grain of sand in an entire desert, a problem of scale and probability. This uneven distribution also complicates experimental timing. Certain experiments rely on the Earth's motion through the galaxy to detect variations in dark matter particle flux. Such seasonal or directional signals are faint and require years of data collection to confirm. Despite these formidable challenges, the search for dark matter continues with unwavering determination. Each failed experiment provides critical data, narrowing the field of possibilities and refining our understanding. These incremental advances are essential steps in the scientific process, building toward an eventual breakthrough. The global effort to detect dark matter involves thousands of researchers, engineers, and theorists working collaboratively across disciplines. New experiments and advancements in neutrino observatories are poised to push the limits of sensitivity even further. Theoretical physicists, meanwhile, continue to develop models that integrate dark matter into the broader framework of cosmic evolution, offering fresh perspectives and potential avenues for detection. The stakes are high. Detecting dark matter would not only confirm its existence, but also revolutionize our understanding of the universe. It could illuminate the processes that shaped galaxies, provide insights into the early moments of the cosmos, and reveal connections between the macroscopic structure of the universe and the microscopic world of particles. Above all, the pursuit of dark matter represents the essence of human curiosity. It is a testament to our drive to understand the unseen, to uncover the forces that bind the cosmos together, and to push beyond the boundaries of what is known. The standard model of particle physics is one of the most successful theories in science. It describes the fundamental particles, quarks, leptons, and bosons, and the forces that govern their interactions. The electromagnetic, weak, and strong nuclear forces. With the discovery of the Higgs boson in 2012, the standard model seemed complete, offering a coherent explanation for much of the observable universe. However, there's one glaring problem. The standard model doesn't account for dark matter. While it elegantly explains the behavior of ordinary matter, it fails to include the mysterious substance that constitutes roughly 27% of the universe's mass energy content. This discrepancy has placed the Standard Model under immense strain, compelling scientists to search for extensions or entirely new frameworks. One of the clearest ways dark matter challenges particle physics is through its gravitational effects. The Standard Model has no particle capable of producing the massive gravitational influence attributed to dark matter. Neutrinos, the only Standard Model particles that interact weakly and are electrically neutral, were once considered candidates. However, their tiny masses and high velocities render them incapable of explaining the observed behavior of galaxies and galaxy clusters. Dark matter's gravitational effects indicate it must consist of a new type of particle, one that interacts weakly with ordinary matter but has sufficient mass to shape the cosmos. This requirement forces researchers to look beyond the Standard Model for answers. Dark matter's invisibility stems from its apparent lack of interaction with electromagnetic forces. It does not emit, absorb, or reflect light, making it undetectable through traditional methods. This property places it outside the realm of particles like electrons or photons, which are central to the Standard Model. The absence of electromagnetic interaction raises profound questions about the nature of dark matter. Does it belong to an entirely new class of particles? Does it interact via unknown forces? These possibilities hint at physics beyond the established paradigm, requiring theoretical innovation. Dark matter's existence suggests that the Standard Model is incomplete. Several theories aim to bridge this gap, including supersymmetry. This theoretical framework extends the Standard Model by proposing a partner particle for each known particle. In this context, the lightest supersymmetric particle, such as a neutralino, is a promising dark matter candidate. However, the failure of experiments like the Large Particle Collider to detect supersymmetric particles has cast doubt on this theory. Hidden sectors. Some models propose that dark matter resides in a hidden sector, a parallel universe of particles and forces that interacts with ordinary matter only through gravity or other weak interactions. This idea introduces exotic particles like axions and sterile neutrinos as potential dark matter candidates. Modified gravity. While not a particle-based solution, some physicists explore the idea that our understanding of gravity itself may be incomplete. Theories like modified Newtonian dynamics challenge the need for dark matter by suggesting that gravity behaves differently on cosmic scales. However, these theories struggle to match the evidence provided by phenomena like gravitational lensing. Dark matter doesn't just challenge the Standard Model. It opens a window into uncharted territory. If dark matter particles are discovered, they could revolutionize our understanding of the universe's evolution, the forces that govern it, and the underlying structure of reality itself. Such a breakthrough might unify disparate areas of physics, from the quantum scale to cosmological structures, offering insights into long-standing mysteries like the nature of gravity and the origins of the universe. Among the myriad theories proposed to explain dark matter, WIMPs, weakly interacting massive particles, stand as the frontrunners. WIMPs are hypothetical particles predicted to have masses much greater than that of protons, yet they interact only weakly with ordinary matter. This means they can pass through stars, planets, and even our bodies without leaving a trace. The appeal of WIMPs lies in their compatibility with the thermal relic hypothesis. In the early universe, particles were created and annihilated in high-energy interactions. As the universe expanded and cooled, most of these particles decayed or annihilated, but some remained. The predicted abundance of WIMPs aligns closely with the observed density of dark matter, making them a compelling candidate. Another promising dark matter candidate is the axion, a hypothetical particle much lighter than WIMPs. Axions arise from solutions to theoretical problems in the Standard Model, specifically the strong CP problem, which involves the behavior of quarks and gluons in quantum chromodynamics. Unlike WIMPs, axions are extraordinarily light and interact extremely weakly with both matter and radiation. What makes axions fascinating is their potential to form a vast, invisible field permeating the universe. These particles could also account for the observed rotation curves of galaxies and other gravitational phenomena attributed to dark matter. Ongoing experiments, such as the axion dark matter experiment, aim to detect axions by searching for their predicted interaction with electromagnetic fields. Sterile neutrinos are an extension of the Standard Model's neutrinos, but differ in a crucial way. They do not interact via any of the known forces except gravity. These heavier, sterile counterparts of regular neutrinos could constitute dark matter if they were produced in sufficient abundance in the early universe. Sterile neutrinos are intriguing because their decay could emit detectable X-rays. Observations of unexplained X-ray emissions from galaxies and galaxy clusters have fueled interest in this candidate, though no definitive evidence has yet emerged. A more unconventional candidate for dark matter is primordial black holes. Unlike particle-based explanations, primordial black holes are compact objects that might have formed shortly after the Big Bang. These black holes could range in size from microscopic to many times the mass of the Sun, and might account for at least part of the universe's dark matter. Although primordial black holes do not require exotic new particles, their presence would profoundly impact our understanding of cosmology and the early universe. Studies of gravitational lensing and cosmic background radiation are ongoing to determine whether primordial black holes could explain the observed effects of dark matter. The diversity of dark matter candidates reflects the breadth of the challenge. Beyond WIMPs, axions, sterile neutrinos, and primordial black holes, researchers explore other possibilities, including superfluid dark matter, a theory suggesting that dark matter could form a quantum superfluid, influencing gravity in unique ways, and fuzzy dark matter, extremely light particles with wave-like properties that could form large-scale structures. Self-interacting dark matter, particles that interact with themselves but not with ordinary matter, could potentially explain certain galactic phenomena. Each candidate represents a different facet of the dark matter puzzle. WIMPs dominate collider and underground detection efforts, while axions and sterile neutrinos push the boundaries of particle physics. Primordial black holes and exotic theories challenge the very concept of what dark matter might be. The search for these candidates is a testament to the creativity and adaptability of science. Whether dark matter turns out to be a familiar particle or something entirely unexpected, its discovery will revolutionize our understanding of the cosmos and the laws that govern it. The discovery of dark matter would revolutionize our understanding of the universe's history and structure. Currently, dark matter is considered the invisible scaffolding upon which galaxies and larger cosmic structures are built. By unraveling its nature, we could answer fundamental questions about how the universe formed, evolved, and reached its present state. In the early universe, shortly after the Big Bang, dark matter played a crucial role in shaping the cosmic web. While ordinary matter interacted with light and radiation, dark matter remained unaffected by electromagnetic forces, allowing it to clump together under gravity. These clumps served as gravitational wells, pulling ordinary matter into them and forming the seeds of galaxies. Discovering the properties of dark matter would refine our models of these early processes, offering a clearer picture of how galaxies, stars, and planets emerged. The universe is structured in a vast, interconnected web of galaxies, clusters, and voids. This cosmic web is shaped by the gravitational influence of dark matter. Without it, these structures would not exist as we observe them today. If dark matter's properties were identified, such as its mass, interaction strength, or particle behavior, scientists could better simulate the universe's large-scale evolution. These insights would bridge gaps in our understanding of how cosmic structures formed over billions of years and how they continue to evolve under the influence of both dark matter and dark energy. Dark matter's role isn't limited to the past. It also shapes the future. The gravitational pull of dark matter counters the expansive force of dark energy, which drives the acceleration of the universe's expansion. Understanding the balance between these forces could help predict the ultimate fate of the cosmos. If dark matter interacts in ways we don't yet understand, it could influence whether the universe continues expanding forever, eventually freezing in a heat death, or collapses in a big crunch. Alternatively, if dark matter decays over cosmic timescales, its diminishing influence could allow dark energy to dominate, leading to even more rapid acceleration and a big rip. By identifying and studying dark matter, physicists could refine these scenarios, offering profound insights into the universe's destiny. Dark matter discovery would unify two seemingly disparate realms of physics, the quantum and the cosmic. At its core, dark matter likely consists of particles governed by quantum mechanics, yet its influence is felt on the larger scales, shaping galaxies and the universe itself. This connection might lead to breakthroughs in other areas of science, such as particle physics. Discovering dark matter particles could expose new forces or symmetries in nature, leading to extensions of the standard model. Astrophysics. Understanding dark matter would refine models of star formation, galaxy dynamics, and black hole behavior. And cosmology, insights into dark matter, could provide clues about the universe's earliest moments, potentially shedding light on inflation or other processes near the Big Bang. Beyond the scientific implications, discovering dark matter would profoundly impact how humanity views its place in the cosmos. It would reveal that much of the universe consists of something fundamentally different from the matter that makes up our bodies, our planet, and everything we've ever known. This realization could deepen our sense of connection to the cosmos, emphasizing that we are part of a much larger, more mysterious whole. Perhaps the most exciting implication of discovering dark matter lies in the doors it could open. Historically, every major scientific breakthrough has led to unexpected discoveries. Electricity paved the way for modern technology, and quantum mechanics revolutionized our understanding of the universe. Similarly, understanding dark matter might reveal entirely new realms of physics, forces, or phenomena that we cannot yet imagine. In this sense, the discovery of dark matter is not just about solving a mystery, it's about expanding the boundaries of human knowledge, venturing into the unknown, and uncovering truths that could redefine our understanding of existence itself. Dark matter plays a fundamental role in cosmology, the study of the origin, evolution, and structure of the universe. Its gravitational influence serves as the backbone of cosmic structures,